In this video, we're going to discuss factorials, which appear in the formulas for many important types of series. A factorial, represented symbolically with an exclamation point, is a function that says that we multiply together all the whole numbers from our chosen number down to 1. For example, if we want to compute n factorial, where n is some whole number, this is the product of n times n minus 1 times n minus 2, continuing on until we multiply by 3 and by 2 and by 1. To compute factorials, we simply have to perform all of the indicated multiplications. For example, in 1 factorial, we need to multiply together all the whole numbers from 1 through 1, which just is the number 1. So 1 factorial will equal 1. For 2 factorial, we have to multiply all the whole numbers between 2 and 1, which would be 2 times 1, and is equal to 2. 3 factorial is 3 times 2 times 1, which is 6. And continuing on, we see that 4 factorial is 24, 5 factorial is 120, and 6 factorial is 720. When working with formulas involving factorials later on, we'll find ourselves having to compute 0 factorial. There's several different ways that we could reason about what 0 factorial might be, but the one that is typically chosen to be correct by convention is the following. Notice that with the factorials we've defined, once we know a factorial, we can produce the previous number's factorial by dividing by our number. So for example, if I have 6 factorial, which we know is 720, I can divide that by 6 to obtain 5 factorial. And this makes sense because dividing 6 factorial by 6 simply just cancels out our 6, and what's left is 5 factorial, 5 times 4 times 3 times 2 times 1. We can divide 5 factorial by 5 to get 4 factorial, divide 4 factorial by 4 to get 3 factorial, divide 3 factorial by 3 to get 2 factorial, and divide 2 factorial by 2 to get 1 factorial. Now, if we continue the pattern in this way, we can divide 1 factorial by 1 to get 0 factorial, the previous factorial in our list, and so 1 divided by 1 is equal to 1. And so under this particular pattern, we're going to see that 0 factorial is going to be thought of as 1. And this is going to, for our purposes, just be a convention that whenever we encounter 0 factorial, we're going to replace it with the number 1. Evaluating factorials is important for many different reasons. However, in calculus, the most important use of factorials is to simplify expressions that involve them. For example, here we have the expression n plus 1 factorial divided by n factorial, and we'd like to simplify this expression to avoid having the factorial involved. In this case, we could start by writing everything out in terms of the product defined by the factorial. So in the numerator, we have n plus 1 factorial, so this is the product of all the numbers between n plus 1 and 1. So we start with n plus 1. We multiply that by that number minus 1, and n plus 1 minus 1 will be n. And then we subtract 1 from that to get n minus 1, subtract 1 from that to get n minus 2, and continuing on until we get 3, 2, and 1. And so n plus 1 factorial is this expression written out here. On the other hand, we have n factorial, which starts at n, and we multiply everything down to 1. So we have n minus 1, we have n minus 2, and continuing on, 3, 2, and 1. And so here we're multiplying all the numbers between n and 1 together. Now, if we look at this as a fraction, we see that there are many factors in common between the numerator and denominator. We have an n in both cases. We have an n minus 1. We have an n minus 2. And right on down the line, we have a 3, a 2, and a 1. And after all this cancellation, what we have remaining is just one factor in the numerator of n plus 1. And so what this calculation here shows is that n plus 1 factorial divided by n factorial is equal to just the number n plus 1. All the other factors in the factorials cancel out completely. Once we see how this simplification works, we could actually then go back and rewrite it in a more compact way. For example, notice that when I wrote out n plus 1 factorial in the numerator, after the n plus 1 factor, the remaining here, everything else is actually n factorial. It's the numbers between n and 1 multiplied together. And so if we then sort of regroup and go back to our beginning expression, n plus 1 factorial over n factorial, instead of writing out all of our different factors, we could note that n plus 1 factorial is equal to n plus 1 times n factorial. And notice here the factorial is being applied just to n, not to n plus 1. Then our n factorials, which is just a number, will both cancel out, and our remaining expression is just n plus 1, as we saw above. And this will be a typical way that we will go about simplifying these factorial expressions. As we saw above, we could always write out a bunch of terms and cancel them, but in many times we're going to simply reduce a factorial in terms of a smaller factorial. So here n plus 1 factorial was written as n plus 1 times n factorial. For another example, let's suppose we want to simplify the expression 2n factorial divided by 2n plus 2 factorial. Notice that the 2n and 2n plus 2 are in parentheses, so we're taking the factorial of those expressions. Again, if we do this in long form, 2n factorial would be 2n multiplied by 2n minus 1 multiplied by 2n minus 2, and right on down the line until we eventually have 3 times 2 times 1. And so here we're multiplying all the numbers between 2n, whatever that happens to be, and 1. In the denominator, we start the same process, but with the number 2n plus 2. That'll be our first factor. We then subtract 1 from that to get 2n plus 1. Subtract 1 from that to get 2n, and then we continue on from there. And right on down the line until we get eventually to the number 1. And now notice that we have, again, several factors in common. We have a 2n in both numerator and denominator, and 2n is just a number. We have a 2n minus 1. We have a 2n minus 2, which is not shown in the bottom expression in the denominator, but it would be the next term before the dots. And of course, we have our 3, our 2, and our 1. And so everything here seems to cancel out except for these two terms in the denominator. So we do have a 1 in our numerator, and in the denominator we have 2n plus 2 times 2n plus 1. And so this would be our simplified expression for 2n factorial over 2n plus 2 factorial. Like in the previous example, we could do this without writing out all of our terms. If we wanted to look at it in that way, we have 2n factorial over 2n plus 2 factorial. And our key observation is in the denominator, where we would start with 2n plus 2. We would subtract 1 to get 2n plus 1. And then everything else, as we can see above, would end up being 2n factorial. We're going to then, the rest of these numbers will be 2n, all the numbers between 2n and 1 multiplied together. And so we could think of the rest of that expression as just 2n factorial. And of course, the numerator we don't have to do anything with. We can just keep as 2n factorial. Those will cancel themselves out. And what's left is 1 over 2n plus 2 times 2n plus 1, just as it was when we wrote out all of our terms. So here is another approach for this particular expression. If you'd like to try a similar example, you can pause the video and try to simplify n plus 1 factorial divided by n minus 1 factorial. Resume the video and see the full solution in a few seconds. If we write out all of the definition of n plus 1 factorial and n minus 1 factorial, we see that we get n plus 1 times n minus 1 times n minus 2 down to 3 times 2 times 1 in the numerator, and n minus 1 times n minus 2 down to 3 times 2 times 1 in the denominator. We have the n minus 1s canceling, the n minus 2s canceling, the 3s, the 2s, and the 1s. And what's left is just an n plus 1 and an n in our numerator. The denominator is now 1 with everything being canceled out. And so we get the expression n plus 1 times n, or if you'd like to distribute that, n squared plus n. Alternatively, we can think of n plus 1 factorial as n plus 1 times n minus 1 factorial, and then cancel the n minus 1 factorial completely, and again being left with n plus 1 times n, or n squared plus n if you prefer that to be distributed out.